Today we're looking again at static rigid bodies, but we're just going to focus in specifically on one type. And today we're going to look at a hinge question. So, what makes a static rigid body question a hinge question? We'll know to use the hinge model whenever the support for the static rigid body comes from a string or a rope or a chain that would have tension in it. So, if tension's involved, we want to use the hinge model. Sometimes the support can come from underneath, and in that case it's thrust. There'll be thrust involved. The other key part is the hinge itself. You'll usually be told that the static rigid body is fixed at one point. It's going to be smoothly hinged at one of its points, and the question will always state that for you. But let's look at the default model. So we want the weight of the static rigid body to be modelled. There's going to be tension going through the string or the rope. And here's where the hinge comes in. And this is massively important. We have a two-part reaction force. These two are connected. One doesn't exist without the other. Because the static rigid body is hinged to the wall, the reaction force can actually go in any direction. It's typically a diagonal reaction force. But we know that we can represent all diagonal forces as a vector, a horizontal and a vertical component. So we're always going to model this reaction force as those two components, the vertical being R and the horizontal being S. As we go through the examples, you'll see why this is important and useful. So, like I said, we might actually have the support coming from below. We're still going to be hinged at a point, and we'll still have the two-part reaction force, the two components of a reaction force, but this time the support is coming from below. It's thrust that's holding the static rigid body in place. Usually, the static rigid body is held horizontally, but we'll come across some situations where it's held at an angle. So, just thinking of the hinge question, here's the default diagram that we must have as a minimum. The context of this question tells us that this is a uniform rod, AB. It has a mass of 70 kilograms and length 16 meters. It's smoothly hinged at A. A light inextensible string is attached at point C, where AC equals 14 meters, and to a point D, vertically above A. The string keeps the rod in equilibrium and in a horizontal position, and the angle between the string and the rod is 20 degrees. All of this can be added onto the diagram. So we know the angle, we know some of the lengths, and we can label some of those points. So uniform rod, meaning that the weight is in the middle, may not look like that on the diagram, but reading the distances, we have a distance of 8 from A to the weight, and we have a distance of 8 from the weight to B. Also added on the 20 degrees, and we know that C is 14 meters. So we know these two lengths, these two distances are 6 and 2. Okay, so the diagram's ready to go. The first thing we've been asked to do is to find the tension. This is usually the first thing you're asked to do in a hinge question. Tension is a force. Now, there are many ways we could find the tension. The tension is a diagonal force at the moment, so it is going to have a vertical component, it's going to have a horizontal component, and we could find it from taking moments. The key here, though, is that there are lots of other unknowns, the R and the S, so resolving either vertically or horizontally is going to need me to use additional unknowns. The simplest way to find T is to take moments. Let's take moments from A. There are two forces involved, the 70G and the tension T. We'll start by considering the 70G. The moment produced here is going to be a clockwise moment, and the way to calculate it is quite straightforward because the perpendicular distance to the force 70G is simply 8 meters. So we are really just doing 8 multiplied by 70G. So the next force to consider is this tension. Now, we need to find the perpendicular distance from point A to that tension. And I'm going to rely on one of these overlay diagrams again. I'm trying to find the distance of this dashed line. I've got the force, I've got the perpendicular distance as a dashed line, and I've got the portion of the rod that helps to form the right angled triangle. So this dashed line is going to be 14 sine 20. So the moment that we have is 14 sine 20 multiplied by t. We can rearrange from here and we get t equals 8 times 70g over 14 sine 20. Alright, all into our calculator and we get 117g or 1150 newtons to 3 significant figures. Next, we're asked to find the magnitude and direction of the force exerted on the rod by the wall. So we're talking about the force made by the components S and R. So the vector SR is what we're out to find. Once we've found that vector, can we find its magnitude? Can we find its direction? To find SR, I'm going to start with components. So the components for T, a vertical component and a horizontal component. I've chosen to draw these components above the force just to minimize any overlap and a bit of a messy diagram. So I'm drawing them above, but I do need to know an angle within this newly formed triangle. Because of alternate angles, we know this is 20 degrees. Each of these components are going to be used. I'm going to start with the vertical. So the vertical forces are 70g and this vertical component. We can say that R plus the component, which is t sine 20, R plus t sine 20 equals 70g. Rearranging that and substituting our value for t, we can say that R is 294 newtons. Okay, can we find S? A similar way, there are only two horizontal components though, S and this horizontal component. We can say that S equals t cosine 20. And once again, we substitute for the value of t we'd already found. S is going to equal 1080 newtons. Okay, so we found R and S, which means we can write out the vector. SR is 1080, 294. If we drew the vector, this is what we would get. 1080 to the right, 294 up. The magnitude of any vector we know we can find through using Pythagoras. So that's 1080 squared plus 294 squared, and that gets us 1120. 1120 is the magnitude. We can use some trigonometry here. So this should be flashbacks to year 12. To find theta, we can use tan, inverse tan, and we get an angle of 15.2. So to describe the direction of this force exerted on the rod by the wall, it's 15.2 degrees above the horizontal. Or if you wanted to describe it as a bearing, it would be on a bearing of 74.8 degrees. Okay, so as always, this came down to a well-drawn, labelled and annotated diagram, and then we relied on 3 techniques. Taking moments, resolving vertically, resolving horizontally, and then a little throwback to year 12, where we had to form a vector, and then we had to find the magnitude and the direction of that vector. Pay careful attention to when you're finding the perpendicular distance to the tension force. That in itself seems to be the biggest mistake that students make. So be really careful there, and that should set you up for success in the follow-through. Now we're going to look at a second type. It isn't as popular, but when it does come up, it throws students off, and too many students are unsuccessful. So I want to make sure that you are well prepared for if it does appear. So this, as I said before, is the type where you're supported from below. And it's no longer tension at play, but it's thrust. This doesn't change much of the question, but it does change your diagram, and you just want to be in tune with the context of the question all of the way through. So let's just talk through this one. Here's the diagram already made, and we're going to go ahead and find the thrust, and we're going to find the magnitude and direction that the force at the hinge exerts on the rod. That's the phrasing that they always use. We're going to find R and S. So firstly, in this question, I actually want to know the distance between the thrust point on the wall and the hinge. So it's A in this diagram that I'm looking for. I can set up all of these lengths using a little bit of trigonometry. A equals 2 over root 3. And you'll see why I've done that in just a moment. So we want to find the moment that the tension force produces. Well, we need to find the perpendicular distance from the hinge to the tension. Let's look at the diagram on its own. Since this perpendicular distance is the opposite of 30, we need 2 root 3 sine 30. That's the perpendicular distance. The reason I needed to find the 2 root 3 is because I knew it was going to be the hypotenuse in this triangle that I've made. So I needed to use that hypotenuse. Let's use that in the moment. The moment is 2 root 3 sine 30 times t. The other moment, the clockwise moment, is going to come from the weight, is going to come from the 40g. 40g is going to be multiplied by its perpendicular distance, which is 5. So 5 times 40g. Some rearranging, and we get t equals 115g, or 1,130 newtons. So that's the magnitude of the thrust that we need. Let's start by resolving vertically these three forces, including this component. We can say that R plus T cosine 30 is going to equal 40G. Rearrange and substituting in our value for T, we can say that R is going to be negative 59.6G. That's negative 584 newtons. What that actually means is that R, we've modelled as going up, but in this particular case, R is a downwards component. So that's not a problem. We just chose by default that R was up, but our calculation has told us that R is actually pointing down. So now we found R, let's find S. Is it actually going to be to the right, or is it going to be a negative value and to the left? At the moment, we have two horizontals that are pointing in the same direction. So when resolving, I'm going to say that S plus T sine 30 equals 0. Rearranging straight away, I can see that S is going to be negative T sine 30. Substituting, S is going to be negative 57.5 G. S is negative 563.5 newtons. So yes, in this case, S is pointing to the left. This reaction force has both a negative horizontal component and a negative vertical component. None of that is going to stop or change what we're going to do from here on. It's just good to know, especially in terms of the context, that our reaction force is going into the bottom left direction. Okay, the rest of the question from here should be straightforward. Once again, we're channeling year 12 skills to respond to the rest of this question. First, let me write out the actual vector. So S is the horizontal, R is the vertical. Let me actually draw this vector. So this is going to the left and down. And we want to find the magnitude of this vector. So the magnitude is going to come from using Pythagoras. Pythagoras, it doesn't matter if the values are positive or negative. I'm going to square them, add them, and square root them. The magnitude of this vector is 812 newtons. The angle is going to come from using trigonometry, and we're using tan. So theta is inverse tan 584 over 563.5. That's 46 degrees. Describing the angle of the reaction force, I can either say it's 46 degrees below the horizontal, or I can rely on bearings, which remove all ambiguity, and say that it's on a bearing of 224 degrees. So, approaching this question on static rigid bodies, a good, well-labelled, well-annotated diagram. We took moments, we resolved vertically, we resolved horizontally, and then we relied on Pythagoras and trigonometry. So a lot went into this question. Taking it step by step and getting yourself enough practice will ensure that you're successful every time one of these questions come up. Okay, Zara, and we're just about finished. But before you move on to some practice questions, let's take a quick look at the specification and exactly what it is that students are expected to be able to show. Exactly what the examiners are anticipating you'll be confident in. While you read through, I want to quickly remind you that it will be sensible for you to come back and watch this video, re-watch this video at a later date. Maybe come back in 2 or 3 weeks or just before an assessment. And as you watch through that second time round, because you've done your practice, a lot of what you go through here should resonate with you much more, and you have a chance to really embed your understanding of the difficult concepts, the ones that I've been flagging up as A star through the video.